So we are looking at molecular dipole moments. Let's take a look at the first structure here. So in order to figure out if a molecule is, or if a compound is bent, we need to look to see if there's a dipole moment. So if we were to look at the bond between the carbon and the oxygen, we can see that the electronegativity is going to draw the dipole to go to that oxygen compound, oxygen atom. And when that happens, these two dipoles are going to converge and they're going to make one net dipole. So you see here in the red, they kind of come together and make one net dipole in this case. And when that happens, we can see that the shape of the compound itself starts to bend. So we figure out that we go from a linear compound to a bent compound. And what we want to see here in carbon dioxide is we're trying to figure out if the geometry, is this going to be a linear or bent geometry? Again, let's look at the bonds between the carbon and the oxygen. And we can see here that in this case, the dipole is going to go towards the oxygen. And when it does that, it's going to make these dipoles kind of go away from each other. And in doing so, they're going to diverge. And when they diverge, you have a linear compound. So this would be a linear compound. With that said, we're going to move on to properties of compounds. And so what I want you to look at is I want you to look at this structure A and structure B. So they both have carbons and hydrogens, but one thing that I want you to notice, and structure C. Let me give you structure C. All right, so structure A, B, and C all have carbons and hydrogens, but I want you to see that this one is linear. This one starts to branch off a little bit on this area. So as you see here, this area, you start to see it branching off here and branching off there. For C, it's completely branched. We have the first carbon in the center, and we have it kind of branching to other carbons. So this is a branch structure. So then what we want to look at in terms of properties, if you were to figure out which one has the lowest boiling point and which one has the highest boiling point. And the way this works is that the branch structure is going to have the lowest boiling point at 10 degrees Celsius. The structure B, where you start to see some branching but not entirely branched, is going to have 28 degrees Celsius. And then at linear, you're going to have the highest boiling point of them all, which is 36 Celsius. And that has to do with the fact that it is more difficult for these bonds to disassociate as opposed to the ones that are completely branched. All right, so let's work through some problems here. So speaking of these bonding and trying to figure out these properties, we're going to figure out the following pairs that we have here labeled 1 through 4. We're going to figure out if it'll exhibit any type of bonding, and we're going to identify the boiling points. So we're going to look at number 1, we're going to look at structure, the first structure, and then the structure, then the one next to it. And we're going to try to figure out which one has the higher boiling point. And then we're going to figure out why it is. So in number 1, we have this structure. I'm going to label it as A and B. So which one has the higher boiling point? Considering what we just learned in regards to boiling points, that we talked about the linear structure having a higher boiling point versus the branch. The branch has the lowest because you want to think of it as kind of like a bubble. And so that bubble is easier to burst and to crack as opposed to something that has more surface area. So something that covers more surface area is going to be harder to disassociate. So both compounds have the same molecular weight. They're actually isomers. So one thing that I want you to notice is that we see some branching here, and this one doesn't. Going back to the point that we were just looking at. The other one is more linear, and this one exhibits some branching, so therefore the structure B is going to have the highest or higher boiling point. All right, so let's look at 2. So this one has how many carbons? Well, it's pentane, so it's going to have 5 carbons. This is a hexane, it's going to have 6 carbons. So because of that, we are looking into play of molecular weight taken into account. So because we have more carbon atoms, we're going to have a higher molecular weight, and thus we're going to have a higher boiling point. So this one's going to have a higher boiling point. See if you can do the last 2 on your own and then come back to see if you got it right. All right, so let's look at these 2, number 3 and 4. So the second compound here, we notice that we're starting to see some hydrogen bonding, right? Because we see an OH bond. And because of that, we know that it's going to have a higher boiling point because of that. This one, the first structure doesn't exhibit any type of hydrogen bonding. So then this one is going to be our higher boiling point. All right, let's look at question 4. So this one goes against, we see hydrogen bonding here, hydrogen bonding there. So they're both the same, but what do we have? We have some branching and we have some linear structure here. So again, because that branching is kind of clustered in one little area, it's going to be easier for those bonds to kind of disassociate than because they have less surface area than the linear. So then this will be our higher boiling point compound. Okay, so that is for properties of compounds and molecular dipole moments.